Right, in 9.3, we're going to talk about hyperbolas and rotation of conics. So what we'll look at is writing equations of hyperbolas in standard form, finding asymptotes and graphs of hyperbolas, using properties to solve them, and then classifying conics. We're actually not going to rotate conics at this time. So first, for our introduction, the definition of a hyperbola is similar to that of the ellipse. So you know that for ellipse, it's the sum of the distances between the foci and a point on the ellipse, which is constant. And for a hyperbola, the absolute value of the difference of the distances is what's constant. So that formal definition for a hyperbola is that a hyperbola is a set of points in a plane for which the absolute value of the difference of all the distances from two distinct fixed points called foci is constant. So if you were to take any point on your hyperbola and go to one focus, and then you go to the other focus, whatever that distance is would be the same thing as if I took this point right here and added that distance plus that distance. So with a graph of a hyperbola, it's not connected. You have two disconnected parts that are called the branches. The line through the two foci that intersect the vertex and the hyperbola, and that line is called the transverse axis. So if you look at this picture right here, your center, change colors a little bit, your center is right here. And your center is always equidistant from the vertices. So if you know the vertices, you could find that midpoint and that would give you the center. And then your foci are always whatever the C value is past that. So we'll work on finding that C value for our foci, and we really have to go past, actually I misspoke there. It's past, the C value is past the center, not the vertices. So if we go from the center out to here and the center out to here, that would be your C value. The center to your vertex from here to here is your A value. So remember when in the ellipses we had the A's, the B's, and the C's. Similar thing with hyperbolas, we'll have A's, B's, and C's. And so again, we have standard form of an equation for hyperbolas, and they will look similar to an ellipse, which is sometimes easy to get them confused. But there's a little bit of a difference between these two equations. So if we look here at the standard equation for a hyperbola, a couple things that you should notice are different. Hyperbolas were always subtracting, where in an ellipse we were always adding. And in an ellipse, your A and your B values switched because your A was always bigger. In a hyperbola, A squared always comes first, B squared always comes second, and A does not have to be larger than B. So remember, in your ellipse, A was always bigger, but in your hyperbola, A does not have to be larger or greater than B. So the A and the B values don't necessarily tell you which way your hyperbola is opening. What tells you that is that if you have your x squared over your a squared, you will have a horizontal hyperbola that will open around the horizontal axis. If your y squared comes first over a squared, then you will have a vertical hyperbola. So you have to look at the top part, if it's x squared or if it's y squared that comes first. That's what tells you the direction of your hyperbola. Your foci are c squared equals a squared plus b squared. Remember that in an ellipse we were subtracting a and b. In a hyperbola we're going to add the a squared plus b squared. So this is just a picture that gives you the two different types of hyperbolas. Again, we have that center is your h and your k. And so to get to that focus out here, if we were going horizontally, we would add c to the h value and subtract c from the h value. If we were going vertically, we would add c to the y value or to the k value and we would subtract c from the k value. So if we look at example 1, we're going to find the standard form of the equation of the hyperbola with the foci at -1, 2, and 5, 2, and the vertices at 0, 2, and 4, 2. So to find the standard form, we need the center and we need our a and our b value. So kind of like an ellipse, sometimes with these problems, when they don't necessarily tell us exactly what we have, it's easiest to just do a sketch and visualize what's going on. So if we have vertices at the point 0, 2, and 4, 2. So we have, I'll go green for vertices. So vertices are here. So we're at 0, 2, and 4, 2. Now something that we know is that the center is always halfway between those vertices. So our center, if we go from 0 to 4, halfway in there is here at 2, right? So our center is going to be at the point 2, 2. So we could write down that we know that the center is at 2, 2. And then they tell us that our foci, we'll go purple for foci, are at -1, 2, and 5, 2. Right? And remember that the distance from the center to the foci is your c value. So if you go from 2, 2 to 5, 2, you went over 3 units. So we know that c has to equal 3. For our vertices, we know that we went from 2 to 4, right? And the distance from the center to the vertex is your a value. So we know that a equals 2. Since you went from 2 to 4, the distance is 2. And we know that since all of this is happening horizontally, that our hyperbolas, if we were to just think about what this is going to look like, our hyperbolas would open around the foci through the vertex, and the center would be somewhere in between them. So they're going to open horizontally. So if we looked at the formula sheets, your horizontal hyperbola will have your equation x minus h squared, since it's horizontal, the x comes first, over a squared, minus y minus k squared over b squared equals 1. So looking at our information that we've already pulled, we know our h and our k, that's from our center. We know a, but we need to find b to figure out what b squared is. So we're going to use the formula for the foci, that c squared equals a squared plus b squared, to help us solve for that b squared. So c squared is 9, a squared is 4, plus b squared. So we get 5 equals b squared. And so now we really have all of our information to write our equation. So we can say x minus h, so x minus 2 squared over a squared. Since a is 2, a squared would be 4, minus y minus k squared, so y minus 2. We solved for b squared was 5, and that will equal 1. So the next thing we have to think about in hyperbolas is that there's actually asymptotes, these diagonal or oblique asymptotes that go through the center of the hyperbola. And if you were to draw a rectangle through your vertices and with your covertices, you would get this square, this rectangle. And if you connected the corners of that rectangle, that would give you the asymptotes. And your hyperbola goes through the vertices and then it follows those asymptotes. So that's really how you know how wide to graph that hyperbola. And so the formulas for your asymptotes, and again, this is on your formula sheet. If you have a horizontal hyperbola, you use the formula y equals k plus or minus b over a times x minus h. Or you use y equals k plus or minus a over b times x minus h if it's vertical. So this b over a part right here, or the a over b part, that's your slope. And the other parts with that h and the k is just the fact that it's not centered at the origin. So your slope will always be that plus or minus b over a, or down here your slope would be the plus or minus a over b if we had to figure out what the slope was. All right, so let's sketch a hyperbola. So again, remember that when we're sketching or coming up with information about a hyperbola, we want the equation to equal 1. So we're going to divide everything by 16 to start. And so we get x squared over 4 minus y squared over 16 equals 1. And when you look at that x squared and y squared, the x squared comes first. So this is going to be horizontal. We know in this case the center, since we're not subtracting an h and a k, the center is at 0, 0. 4 is our a squared. So our a values are the vertices. So our vertices will be a to the right and a to the left of the center. So we'll say our vertices are at plus or minus 2, 0. If we're talking about co-vertices, which is your b value, your co-vertices are going to be on the y-axis, and those are going to be at 0 and plus or minus 4. Since 16 was your b squared, your co-vertices are your b value. And then we need to find the asymptotes. So your asymptotes for your horizontal hyperbola, remember, are the equation y equals k plus or minus b over a times x minus h. But when x or k and h are 0, we just get y equals plus or minus b, which is 4, over a, which is 2, times x. Or we would say y equals plus or minus 2x would be the equations for your asymptotes. So now when we graph this, we'll start by graphing our center at 0, 0. Our vertices are at 2, 0 and negative 2, 0. Our co-vertices are at 0, 4 and 0, negative 4. So now you can either graph the line y equals plus or minus 2x, or once you have the a and the b, if you were to draw just a dotted rectangle around that connects your a and your b as sides of the rectangle, then what happens is that if you were to draw diagonal lines through the corners of that rectangle, through the center of your hyperbola, that is the equation y equals plus or minus 2x. So instead of actually having to graph a line, and then all you have to do is remember that you're graphing a horizontal hyperbola. And so your graph just follows along the asymptotes. It hits the vertex and it follows back along. It should not go through the center. It only goes through the vertices. So it would look like that. And remember, you want to use all of that space that you have with those asymptotes. So in our next example, we're going to find the asymptotes. So we're going to sketch another hyperbola and find an equation of the asymptotes. And we're also going to find the foci, which we didn't do in the last one. And so if you notice here, they don't necessarily give us information, but they give us this equation that we're going to have to put into standard form. So we first start by grouping our x's together. 4x squared plus 8x. We just have a negative 3y squared, and we move the 16 to the other side. So remember, when we start to complete the square, we want, in this case, the 4x squared to have a leading coefficient of 1. So we're going to factor out a 4, and we'll have x squared plus 2x. And to complete that square, we're going to add b over 2 squared. So if we add, our b value is 2, 2 over 2 squared. This minus 3y squared can stay because there's no y, and that's going to equal negative 16. But remember, we're adding 4, and this 4 is being multiplied by this 1, so we're really adding 4 to the left, which means we're adding 4 to the right also. And so if we simplify this, we get 4 times, this is x squared plus 2x plus 1, minus 3y squared equals negative 12. And if we factor that, we get 4 times x plus 1 squared minus 3y squared equals negative 12. And so remember, for hyperbolas, if we want to put them in standard form, we need them to equal positive 1, which means we need to divide everything, in this case, by negative 12. And so when we divide everything by negative 12, we get negative x plus 1 squared over 3 plus y squared over 4 equals 1. But with hyperbolas, this first term can't be negative. It has to be positive. So we have to switch the x squareds and the y squared. So we're going to say our equation is actually y squared over 4 minus x plus 1 squared over 3 equals 1. And so by doing that switch, now we know that y squared is coming first. So we have a vertical hyperbola. And so if we're looking at this, if we're graphing this, we know the center. If we look at the center, our h is always with the x. So our center is at negative 1, 0. In this case, our 4 is our a squared. So our a equals 2, and our b would equal the square root of 3 if we needed that. So for our vertices, because this is vertical, our vertices are going to go up from the center and down from the center. So our vertices, we're going to add and subtract 2 from the y coordinate. So our vertices will be at negative 2, 2. Oh, not negative 2, sorry. Negative 1, 2. And then we'll be at negative 1, negative 2. And again, if we were starting to put this on the graph, if we had the point negative 1, 0, because it's vertical and our a is 2, we would go up 2 from there and down 2 from there for our vertices. And maybe we should color code it. So our vertices are going to be green. So our vertices would be here and here. And then our co-vertices are at root 3. So we know that root 3 is just a little bit less than 2, but a little bit more than 1. So if we just did a quick little sketch of where our co-vertices were, we would kind of go over here just for drawing our hyperbola, because then remember, we can draw that box around using the vertices and the co-vertices. This corner over here is not very good. And then if you were to sketch the asymptotes through there, you would have the asymptotes. So you don't necessarily have to have your equation to draw your graph. It does ask for the equation. And then keep in mind on this one that this is vertical. So when you have those asymptotes drawn in, it really could go either way. So you have to remember that you're going through the vertices. So on this one, we would have a vertical hyperbola, and it would have to open up and down. Now we still have to find the asymptotes. And so remember your equation for asymptotes for a vertical hyperbola are y equals k plus or minus a over b times x minus h. Okay? And our center is negative 1, 0. So our h is negative 1 and our k is 0. So when we're writing these equations, we could say y equals, since k is 0, we don't need the k, plus or minus a, which is down here, we know is 2. B was the square root of 3 times x minus a negative 1, so x plus 1. And so that would be the equation for those diagonal lines that we graphed. So eccentricity for hyperbolas is still the same. You calculate it the same way. E equals C over A. But for a hyperbola, your eccentricity has to be greater than 1. So if you had a problem where they said the eccentricity was 2, you would automatically know it's a hyperbola since that value is greater than 1. So in our next example, we're going to use the asymptotes to help us find a standard equation. So we have standard form of the equation of the hyperbola. They gave us the vertices. So again, if we were to just do a little sketch to help us figure out, is it horizontal, is it vertical? We have the point 3, -5. So if we have the point 3, -5, and we have the point 3, 1. So these are the vertices, which means then remember that the center is halfway between those. So between -5 to 1, that's 6, which means the center is going to be up 3 and down 3. So this is your center right here, which is going to be at the point 3, -2. Right, so if we know that the center is at 3, -2, then what else we could figure out too is your vertices or your A value. Because your A value is the distance from your center up to your vertex. And in this case, your A value is going to be 3, since the distance from the center to the vertex is 3. And to write a general equation, we need to know what the center is, we need to know A, and we need to know B. So the way that we're going to use B is with this information about the asymptotes. So if you look at your asymptotes, if you notice, their slopes are +2 and -2. And remember we talked earlier about the slope of asymptotes. And again, I guess we could go back to this sketch here. And if our vertices are vertical, right, then we know that our hyperbola would be a vertical hyperbola. So for our asymptotes, the slope, if we went back to the formula, the slope is that plus or minus A over B for the vertical hyperbola slopes for the asymptotes. And so since in this case we know that this would equal your slope, we know that the slopes are plus or minus 2, so we could say that plus or minus 2 equals plus or minus A over B. And what happens is when they're both plus or minus, we could just say that 2 equals A over B. And we know that A is 3, so 2 equals 3 over B. So if we solve for B, we could say 2B equals 3, which means that B would equal 3/2. So now we have that B equals 3/2. And so now if we need to write an equation, our standard form for your vertical hyperbola, remember we're going to have the y minus k. So we're going to have y, and this is your h, and this is your k. So y plus 2 squared over a squared, since a is 3, a squared is 9, minus x minus h, so x minus 3 squared over b squared, and this is just going to be a fraction, so 3/2 squared is 9/4. It will equal 1, and we'll just leave it like that. And then the last concept here is when you're given the general equation, the ax squared plus bxy plus cy squared plus zy, all of that information, if you can compare the a and the c terms, so looking at the a term is the number that's in front of the x squared, and the c term is the number that's in front of the y squared. And so for this, and again, this is on your formula sheet, so you don't need to memorize it. If a and c are the same, then the conic is a circle. If you multiply a and c together and get 0, so really if a is 0 or c is 0, but not both, then you get a parabola. If a and c are positive, you get an ellipse. And if A and C are negative, you get a hyperbola. So we'll go through a few examples here. So let's classify the graphs. So first, let's just identify what A and C are. So remember, A is in front of your x squared. So for part A, we know that A is 4. We don't have a y squared, so we would say that C is 0. And so in this case, if we do A times C, we would get 0. And we know when A times C is 0, we would have a parabola. If we look at part B, we know that A is 4 because that's in front of the x squared. Your C coefficient is in front of your y squared, so C is -1. If you do A times C, we would get -4, and -4 is less than 0. So when you do A times C and you get something that's less than 0, then that means that you have a hyperbola. If we look at the next one, letter C, here if we look, our A is 2 and our C is 4. And so if we do A times C, we get 8. 8 is positive or greater than 0, which would mean that you have an ellipse. And if we look at letter D, our A is 2 and our C is 2. So don't get caught up in if I multiply them together, it's positive, it's an ellipse. Remember that if they're both exactly the same, it's a circle.